Hello, good morning or afternoon, everyone. Hi, Dr. Clezio. We are here today for a very special talk given by a very special guest, Dr. Clezio De Nardin. He earned his degree in electrical engineering from the Federal University of Santa Maria in 1996 and his PhD in space geophysics from INPE in 2003. Since 1997, he has been a researcher at INPE, where he served also as director. He has published over 100 articles in international journals and has received 16 scientific awards. Dr. Clezio has held leadership roles in various scientific organizations, including President of the Brazilian Society for Space Geophysics and Aeronomy, Vice President and later President of the Latin American Association of Space Geophysics, or ALAGE, and Deputy Director of the International Space Environment Service. He has also represented Brazil in international bodies such as the World Meteorological Organization's Space Weather Team and the United Nations Committee on the Peaceful Uses of Outer Space. Today, he's going to talk to us about the Brazilian space program and INPE satellites due to the CANSAT World Competition. Thank you, Dr. Clezio. Please have the word. I think he's not allowed to turn on the mic. Could we give him permission? Okay, let me see.
Okay, then.
Great, thank you.
Let me first ask you, you want me to speak in English or you want me to speak in my Spanish?
English, please.
Okay, then. So let's start presenting. Let me... Okay, this is the presentation. So you see my presentation right now?
Yes.
Okay, so let me start saying that I'm not seeing you because I'm in front of my presentation now. So if you like to make questions, I don't know if we'll be addressing the end, or either you can raise your hand. I don't know if it's going to appear here to me. Anyway, I'm going to try to give my speech in something like 30 to 40 minutes, and we'll have time to talk afterwards by the end of the meeting, okay? So let me start saying that it's a really, really pleasure to be here. I'm a very excited to see that Mexico is starting, not starting because you have already some satellites and CubeSats in the past, but now UNAM is reactivating the satellites and the government of Mexico is pursuing this satellite development for Mexico. I think that is the next step to the big countries in the world is to be part of, to have access to space. Meaning, if you do not have access, if you do not have assets in space that you control, you build, or you are part of the building, you are not a big country. That's the new issue. And I compare the access to the space to the access to the navigations in the early 15th, meaning those countries that could navigate in the deep water, they were the power at the time. Currently, the big countries are those who have access to space and they can build access, or they are important players with space. So that said, I'm going to talk about space mission program. As you know, I was former director of INPE recently, but my background is I'm a space scientist, and I have been director of INPE for the last 5 years. So I'm going to talk a little bit about the multi-mission platform that we developed. We start in the early in the 16th, and we finish by 2020 when we launch the Amazon 1 satellite. But I'm not going to talk about the past satellite. I'm just going to talk about the Amazon 1, the multi-mission platform, which is very much attached to the Amazon 1 satellite so far, because it is important to understand what we're going to have for the next missions that are going to present them. Thereafter, I'm going to show the missions that we are developing right now. INPE is currently developing Aqua mission, CIBER 6 mission, the CO2 imager mission, in the CIBER 5 mission, the meteorological satellites. Besides that, we also have small sat missions, which are not CubeSats, are developed platforms at INPE. Okay, let's start them. The multi-mission platform. Multi-mission platform, as currently known, the P250, meaning it is a 250 kilograms platform. With that platform, we can have satellites of about 1,800 kilos, 700 kilos, almost 1 ton. Depending on the mission, depending on the target they're gonna focus your mission, you can degrade a little bit the platform, and you can have up to 1 ton satellite. Currently, we have launched the Amazon 1, which is 780 kilos, meaning almost 800 kilos. So the concept behind this platform is key to understand what are the next missions that we're going to launch. The multi-mission, why do we call multi-mission platform? Because we developed the platform in 2, like Legos, parts. The first part is the bottom or the upper part, depending on the orientation of the satellite, which is half of the satellite, which is the control unit of the satellite. I mean, not the payload. Everything but the payload is the controlling system of the platform. So all the controls are set together in one half of the satellite. There you have the reaction wheel, the control bus, and including the instructor. This instructor that you see here in this view graph in the right side of your view. You see this instructor here is also designed to be launched with different satellite operators. I mean, the launchers operators. Meaning, the platform was conceived, project, and designed to react to several kinds of launches. Meaning, the figure of launches, the vibration figures of launchers was overlapped to create an envelope of vibration of which the platform, the P200, P250, is resistant to. Meaning, we can launch in the Vega 2, the Vega launcher, the Taurus launcher, Eurococket launcher, the DN Hyper launcher, and the Delta 2 launcher as well. Besides the PSLV. So the platform was designed to fit inside the cover of the head of the satellite, of the head of the launcher, of all the commercial launchers available. So we design it with the specification that fits in the different launchers. So fits in the different kind of launchers. So we can take advantage of the different launchers available in the world, and we can launch the satellite with the less price as possible, since Brazil doesn't have his own launcher so far. And I'm going to show in the next slides that Amazon One, which uses this platform, was launched in PSLV on February 2021. And it was solar synchronous orbit launched from India in the Sriharikota space base. But the point is, all the systems, all the reaction wheels, all the consumption of the battery, all the connections, all the redundancies were designed to be compatible with any kind of payload that you would like to attach it to this bus. With that philosophy in mind, we spent several years to develop that. We could launch Amazon One. This is the Amazon One, as you can see here. We are seeing you are seeing pictures of our laboratory for integration, assembly, and integration test in Brazil, here in São José dos Campos, here at INPE. And you see here in the red part, in the front, very front of this picture, the shaker, and you have 3 of those shakers here. And you also see in the back of the photo, besides the antenna, just aside of the antenna, the chamber that I'm going to show you where we put the satellite to burn a little bit for the cycling of the thermal cycle of the satellite. You have also small chambers. This is a chamber that fits up to 2 tons satellite, 2 toneladas. So this is the structural qualification. So we shake all the satellite together. You see that you have the dummies of the panel inside our stall in the satellite. You have also the camera, as you can see, in the middle of the satellite, very close to the bus. And then the communication antenna, which is the round one in the upper part of the picture. This is the thermal qualification. The satellite is ready to be put in the chamber. There you can see in the back of the photo, you see the chamber. The doors are still closed at this time because people are assembling the cables to heat the satellite. So that's the back view of the satellite Amazon One. Nobody take pictures of the back view, but since you are engineers eager to make your own satellite, I figured out that it's going to be a good picture to you. And then you have 2 cameras here to field of view. So this is for heating the satellite. You also have the heaters that are put together with the satellite. So this is the wire, and then you can see that. This is the electromagnetic verification. People call AME and AMC, coupling and interference of the satellite. So you see you don't have all the protections, the thermal protection of the satellite where we take it out. And you also see the panels, the solar panels are not attached to the satellite. But there, you can hit the satellite with different kind of frequencies. And you can investigate which kind of circuit will give you the proper or right answer according to the specification of the test that you develop during the operation of the satellite. So we put the satellite in this kind of EMC chamber. These are electromagnetic shielded cameras, and then you bombard the satellite with different kind of frequencies that you expect to see in the lifetime of the satellite. And then you check all the codes and all the tests. You do all the tests with your commands of the satellite, trying to figure out if you have any kind of interference in your circuits. The other part of the test here is testing what are the figure of the satellite into the environment. So you turn it on, all the satellite, or you turn on some sub-circuits, you turn on the heaters, you turn on several parts of your satellite, and you check whether or not you're going to have interference, magnetic interference in your circuits. So meaning you are interfering in yourself. You are emitting radiation to yourself or to the environment where you are. So we do also this kind of test, and we did. This is the another system verification. This is the polarity verification. We check here, two tests are carried out here with this kind of white structure that we have there in our lab facility. We test like when you are trying to figure out the balance of your wheels of your car. We do the same with the satellite. We balance mechanically all the satellites. So we balance it in 3 axes, in the vertical, and we, of course, we attach the satellite in the different ways to this kind of structure. And we spin the satellite to check the balance here. We also do magnetic verification, magnetic interference, using some coils around the satellite, which is, in this case, this white structure is just used to grab the satellite in the place in between the coils. So we check for interference, magnetic interference from the satellite, I mean the magnetic balance of the satellite. If you turn something and you may have magnetic interference, not the electromagnetic that are generated by currents, but in this case, the interference of the battery on or the whole satellite as a steady state use. So we check for, let's say, continuous operation of the satellite, and we see if they have any kind of magnetic interference around. This is another system verification, but that's a small room that we have attached to the big room that you saw in the other pictures. So you saw in the previous pictures, what you saw was the big room for building those tests, environmental tests of the satellite, like the vibration, like the thermal, the validation, the cycling, and then the final test, the system verification, we perform in a more specific room. That room that you saw previously is a class 100, meaning is 100 particles per 1 square inch of space, meaning you have less than 100 particles, dust particles per square inch, or cubic inch instead of the environment where you are testing your satellites. In this one here is a class 10,000. We have less than 10,000, I mean, it's 1 order of magnitude better than the previous one. And we use to test, to do the electrical verification in this room because the satellite stays too longer open. We have to open the platform for a longer period of time. And due to the exposure of the platform, we prefer to make the electrical verifications in this kind of room. So here you see in the upper part, this is Amazon 1 again. I'm still using the Amazon 1 to talk about the platform to P200. When you have here is the upper part, of course, is a dummy. The upper part here is a dummy. Only the computers are there. We did not install the payload yet. We just check the payload separately. But the point here is to check the platform. So the bottom part that you see, like petals of a flower, it's the platform. The platform opens like 4 petals. So you can have 90 degrees excursion of the panels, the lateral panels of the platform. And then you can see in very front of you, the computers. You see there the black round stuff in the bottom part of the inner box that you can see through. You see the reaction wheels. You have 4 reaction wheels. And then you have the computers, and you have the umbilicals attached to the computers. So here we check all the electric connections. Every single electrical connection is checked by computer and manually. It's more than 14,000 connections for these kind of satellites. There is a kind about of 6 kilometers of wires inside the satellite, and every single connection is checked manually and computer connected, meaning we send commands to the computer and we expect the computer reaction in such a way, and we confirm or not the well behavior of the computer. This is a kind of 2,000 hours of satellite power on in this kind of configuration. It is a 24/7 test verification before launching. The other system verification is the polarity verification. That's what I was mentioned where when we were talking about the electrical interference, and I mentioned that close to that white part there, where we check the balance of the satellite, the 3-axis balances. We also have, and I mentioned before, that we also have the magnetic interference. So in this case, the satellite is pre-assembled. The only thing that is missing here are the thermal barriers around the satellite, those yellow envelopes around the satellite. All the rest is ready for launch. So what you see here, this not black, white, these white panels, these white tubes around the satellite are indeed magnetic coils. So we measure, when we turn on a subsystem of the satellite and we measure in 3 axes, which is the magnetic field, not the magnetic field that is being generated by that subcircuit and where it is acting into the satellite. So meaning we know exactly the field, the magnetic field created by every subcircuit of the satellite. And this is the kind of test that we do. And this again is in the clear room P100, meaning, the room class 100,000 particles per square inch. So when we finish all the tests, then we assemble the satellite and pack it to be launched at the base where it's going to be launched. In this case, we are seeing pictures of the day before. You are seeing pictures here of the day before the launching of the satellite from the Sriharikota, the Indian base in the southern of India, in Chennai. So this is the Amazon 1. And you see the bottom part of the satellite here. If you are seeing the mouse, I'm pointing here. The bottom part is the platform, the P 250 kilograms. This part here, only this part is P 250 kilograms, including the panels, including the cameras, the all sky cameras for star tracking cameras, and the heating pipes. Everything here is controlled by this small box in the bottom of the satellite. And then you have the ring that attaches the satellite to the rocket. And then you have the bottom part, which is the rocket here. So the upper part here, is the box that actually does the mission. So this is the satellite. This is the brain of the satellite. And this is the mission we develop. And this kind is a imager satellite. In the infrared, in the near infrared for crops, and high resolution cameras. And you see here in the back the communication antenna, because it flies in the with a small area ahead and looking downwards to see to make earths of the image of the earth. So this is the last configuration. This is the last thing that you see before your satellite being launched. So this is the picture from the base attached to the satellite in Shirahikota in 2021. This is February. These are the images to have an idea of the satellite. The satellite is already launched. We have completed 4 years of mission so far, which is the 100% of the mission already. So we designed a satellite to be operated for 4 years, and we fulfilled. It is operational for 4 years, and we recalculated the lifetime of the satellite based on parameters that we measure for the tracking control of the system that we have here in Brazil. And we estimate that they're going to have another 4 years of operation with the same satellite without spending a dime. Meaning, all that we need is the team that is currently operating satellite. They're going to be operating for another 4 years. So this is a new target now. So we complete the mission. We fulfill what we expected to be the mission of the satellite. So it's since last February of this year, the mission is a complete success because we built, we launched, we acquired the imagers, and you can see here the Bahamas and Florida, and we operated for 4 years. And it was developed. That was we promised to the government, and we fulfilled. So the bonus now came, and we have 4 years more. So we got the money for the next 4 years, and they're going to be operated for another 4 years. And still, we are building new satellites. But before that, let me mention here, this is here shades of white. I'm not going to show all the images because I have several of those images. The purpose here is to talk about missions, not about imagery. So this I pick for as an example of what we can do with the satellite. Now let me go ahead with that. So we now have in mind that we have a very good platform that is made to be launched in several launchers, meaning the price for launch is going to be down because we're going to have competition for launchers. We don't have to be attached to a single launcher. We are not obligated to launch with some specific one. We can launch whatever we want. And we have the whole control in our hands. Now what we have, you just need the upper part or the bottom part of the satellite, which is the payload. So you can unattach one payload and put another one, and you change completely the mission. So meaning this platform can be used for several missions, can be used for image, can be used for communication, can be used for SAR, can be used for visible lights, can be used for a GPS constellation, can be used for science purpose, for monitoring space weather, wherever you want. We have now a satellite that we know how to do, and we can carry up to 500 kilos with our platform. It's like to have a small truck. You have all the truck, you just don't have the load of the truck. If you are going to load wood, you have one kind of the load. If you're going to sell ice cream, you have another kind of the load of the truck. So that's what we did. And now we are currently develop a mission with Argentina. So Brazil and Argentina are cooperating to have the Amazon 1B, which is part of the Aqua mission. What is the Aqua mission? It's a mission that also monitors the water resources. You saw from the previous images that we can have different shades of blue, different kind of chlorophyll measurements. And we are increasing the power of the Amazon 1, creating the Amazon 1B by including a GNSS-R, meaning reflectivity. We use the GNSS system that send those signals to the Earth and reflect on the surface of the Earth. and we collect the reflection of the GNSS in the satellite, not the directly measurements of the GPS. We measure the reflection of the wave of the GNSS hitting the ground and going up to the space again. And based on that, we calculate humidity, winds, and flood area. We monitor flood areas. This is to be delivered in 2026. By next year, we're going to launch another satellite with Argentina in this case. The other satellite that we are doing is the CIBER-6. CIBER is a cooperation that we have with China. So Brazil and China have launched several CIBER satellites, several, up to 4A. It's a kind of 6 satellites being launched with Brazil and China. There is a 3B, 4A, that's why they make 6. Now the CIBER-5 is going to be launched before CIBER-5. So why 6 launch before 5? Because, again, since we develop a multi-mission platform, we would like to stress the platform to the best to know what is the performance. So we are now attaching a different payload to the same platform. Remember, Amazon 1 was PMM with a visible light and ultraviolet and near infrared, but visible. All using solar synchronous orbit, all taking the sun as a source. The Aqua mission with the Argentinians, again, but we also use the GNSS reflectivity being measured at the satellite. And the next one in 2028, we're going to use the satellite is going to power down the emission antenna, and then we're going to receive the back signal, meaning we are developing a SAR remote sensing satellite. And those are the resolutions that, these are the resolutions that you can have in the X band, 9.3 gigahertz. We have 4 polarization, and in this leading point, we can have 1 meter resolution with this kind of satellites. Again, we develop the control, all the satellite control, all the satellite attitude, all the satellite power bus, everything is on us. And the payload is going to be developed by the Chinese side. Meaning, we can have a payload that, we can have a bus that can be attached to every payload that you want, up to 1 ton satellite. And this new satellite is also increasing the power capability. We are increasing like 20 to 40% of the power possibility of power supply of this satellite in regard to the previous version. Meaning, our platform, our P250, is the best performance platform for this class of satellite in the world. Nobody hits our power level. We check that online, but of course, maybe some military satellite that we don't have access to. So I'm talking about civil satellites. Again, now come back a little bit. Let's stop a little bit. I'm coming back to the CIBER-6 to talk a little bit before going to the next slide. Okay, we have a P200, meaning a platform that 250 kilos that can hold satellite, traditional satellites. We can also include GNSS receivers into the platform and use for reflectivity. We can increase the power, stress the platform to the maximum and use it as a SAR X-band satellite. So you're improving the same satellite, the same quality platform. Now the question comes, okay, why don't we shrink it? Why don't we reduce the size of the platform without reducing the quality? So we did, and we create the P100 platform. So instead of having 250 kilos, we develop a new platform. The new platform weighs 100 kilos, less than a half of the previous platform. And then we have different configurations, the P100 Alpha and the P100 Beta. I'm going to talk about that about that different later in a few slides ahead. For now, I'm gonna say that in 2029 we're gonna launch it. We're gonna launch the new satellite, the new payload P100, mission that is designed to qualify and monitor the greenhouse gases. It's a laser instead of imager. People, of course, you have greenhouses measurements from the space. We see CO2 imagers and NH4 imagers from the space, but they use imager. They used to have the sun as a source, and they make image, and from the image they process that, and they have an idea of the CO2 emissions. Instead, in a partnership with the DLR in Germany, INPE developed the CO2 imager mission, meaning a laser point. So what you see here is the CO2. This is a laser, very precise laser, like the pointers that you have for presentations. So this kind of laser, it shoots down a laser pulse and recovers with the mirrors into the satellite, considering all the flight configuration and all the flight movements. So everything taken into account, we collect the data that we send down with a laser pulse, and we collect ahead, and we have a measurements of the CO2 with a very, very high resolution. This is under development. Is this to be confirmed? But we have the money already, and the Germans are with the mission also in very tiny schedule, because they are almost finishing their part of the mission, which is the payload. And this is decided to where to be launched yet. We don't have the launcher again. But again, since we developed like the previous platform, we now have a platform that can be launched for everywhere. What is the advantage of this platform instead of the previous one? This platform is half of the weight of the previous one, with roughly the same power supply. So meaning, instead of pay $28 million for launching, we're going to pay only $4 million for launching. One launch of this platform, it costs a fraction, 20% of the previous launcher. Meaning you can launch with the small vehicles instead of the big ones. And it reduces a lot the costs of developing the systems and subsystems, because they are teeny tiny. So you can also pay as a secondary payload in the satellite. Is going to be cheaper and even cheaper. So the estimate to build this satellite is not a half of the price of the previous one. This is 1/3 of the price of the building. The platform is 1/3 of the price of the previous one, which is about $10 million for building, $10 million US for building the platform alone. And finally, what about the CBERS 5 that we skipped? Remember that we developed CBERS 6 before the CBERS 5. So the CBERS, the 6 before the 5. So what about the 5? We redesigned the 5. 5 is going to be a geostationary meteorological satellite. The payload is under evaluation, but we probably going to have an imager there, a EIR sounder, a greenhouse sounder, an ocean color imager, and some scientific experiment, most probably attached to the space weather issues, like a coronagrapher, like a particle detector, or something from the space. And that's going to be the first Brazilian full developed geostationary satellite that INPE is going to be put in charge of the payload, the bus. So we're going to have to control with a very precise and radiation cost-effective shielded circuits, because it's going to be 36,000 kilometers away from the ground sea level, instead of the 750 kilometers, 750 kilometers away. That is Amazon 1, and we are used to do that since like the 30 years. So again, this finished the big satellites. Now I'm coming to the end of the presentation. I need 2 more minutes to finish, and I would like to talk about, okay, what about the small satellites? Small satellites are also being developed at INPE, but not CubeSats. Again, we developed the P250, we shrink it to fit P100. So if you shrink again a little bit more, so we have the P30. And if you shrink a little more, you have the P10. See, based on the knowledge that we developed with the P250, we now are able to reduce the platform and optimize the bus so we can carry different kind of missions. The P30, for instance, is designated to be the platform to the Turisat. Turisat, it's a camera to look for fire spots. It's a fire monitor. Instead of have a huge imager, you process that, taking spots, hot spots in the imager. You have a fleet of satellites, very cheap. You can send hundreds of those. You can send tens of those because they are very, very cheap. They are P30. They are 30 kilos platform. So they can have 100 kilos, 30 kilos platform can hold twice his weight in carrying load. So you can have, let's say, 90 kilo satellite. So you can hold a 30 or a 50 or 70 kilos camera. So you can have several measurements of the fire, and that's what we did. So we developed now a satellite P30, a platform that can be attached, and the first one is designated to be the fire monitor. Similarly, you know that you have several small cameras that have been used in CubeSats. So why don't you use these cameras that has been now space qualified to put in our own platform? I'm not buying any Danish platform. I'm not buying any American platform. We develop the platform. We're not assembling a satellite. Of course, we do assembly, but we assemble our own project. We develop the project of the satellite, and we are designing the P10 to be the first biome monitoring. It's a camera, like the Amazon 1. So you can have the revisit of the biomes much more frequent than we have currently. So again, what is missing in the presentation is what I mentioned to you, that we have the P100 was designed with the alpha configuration and beta configuration. What is the difference between alpha and beta? Is this one here, the upper satellite, the 4 missions in the upper part here are attached to the alpha configuration. What is the alpha configuration? The solar panels are fixed. Why do you have fixed panels? Why don't you have only mobile panels? Because of the vibration of the movement of the satellite. So the pointing precision, to have very good pointing, you have to have stationary panels. So those missions that do not require moving panels can use the alpha platform. So like SAR imager, like SAR umbrella, this is a SAR with an offset type antenna. I'm talking about from the left to the right, the upper 4 satellites around the P100 alpha. So there you have the SAR with an offset type antenna, the SAR with an umbrella antenna, you have the SAR with the planar antenna, and you can also have the optical satellite. So these are very good pointing precision satellites. But if you if you can neglect a little bit the pointing, and you can have a wider field of view in the space, you can use the beta, like the monitoring of the solar bursts, like monitoring the big collapse of the black holes, this scientific mission not called MIRAX, like the MIRAX mission that we have here at INPE. So we are looking for X-ray coming for the collapse of 2 black holes. that give rise to the Einstein gravitational waves. So with that, you can use the beta P100 beta. Or if you like to have a equatorial, like the EQUARS, the equatorial mission for monitoring space weather, that you can have different measurements that are scientific measurements that they don't need really, really good pointing precision. You can neglect a little bit of the point and have a wider field of view. You can also have the P beta. The conclusions, well, meaning, I'm closing the presentation right now. We have relevant missions in Brazil, that would be being implemented under the evaluation, all the missions using medium and large satellites for international cooperation. A compromise is our search between meeting Brazil's strategic needs and the technology development of the industry and industrial development. The concept of the multi-mission platform has been validated by the PMN. This is very, very important. We validated, we flew it with the Amazon one. And then we shrink again, and we are going to validate the P100 in 2029. Thank you very much for your attention. If you'd like to contact me, this is my email. I'm the National Institute for Space Research, INPE. And if you screenshot your view graph now, you can scan this QR code and you find me in the ORCID platform. I think that's it. I'm now open to the questions that you may have.
Thank you. Thank you so much, Dr. Clezio. Amazing talk. Does anybody have a question?
Here. Hello, Clezio. I'm Alex. Do you hear me?
Yeah, a little, very far away, but I can hear you, Alex.
I'm coming next to the microphone. I'm Alex. We were chatting early in the morning. And well, I'm glad to know you and about your presentation. It was fantastic. I am happy about what you have been doing in Brazil. So congratulations. It's shocking. And well, I have a question for you about your expertise and about your knowledge. Which has been the most difficult issue to attend to develop your space program in Brazil?
There are two big, thank you very much for the question, Alex. There are two big issues. We have several. Work with the space is not easy and it's not cheap. When I talk about missions, I'm not talking about hundreds, I talk about $1 million. But that's not the worst part. Countries like Mexico, like Brazil, like Argentina, we do have money. Money is not an issue. There are two big issues besides having money. First one is political issue. You have to have a huge and a target space agency, very, very focused, decided, and a political decision to do that. When you have a political decision to do that, you can easily pursue. Then you have the only issue to solve, which is the second one. So the first one have the political decision. This is very, very rare in developing countries.
Yeah.
And it's easier to have in developing countries in Europe because you have ESA embracing all the other small countries, underdeveloped countries in Europe. The ESA supports them and they bring them together. They attach it to the big 3 or 4 space agencies in Europe. So it's easy to them to have access to this technology. For us that are flying alone, like Brazil, like Argentina, like Mexico, that's a newcomer with the Mexican Space Agency that I've been new that this year they disassemble something like that. They disassemble the Mexican Space Agency or so. The very newcomers to the field, like us, like Brazil, like Mexico, like Argentina, like Peru. The second big issue after having the political decision, is have access to quality components, not subsystems. Subsystems we can develop. We can develop systems, we can develop subsystems. We know how to design, we know how to project, but we don't have access sometimes. Yeah. And sometimes we have embargoes against here and that. They don't give you the best issue. And I can testify that in the past, I'm not telling who, and I'm not going to telling for which satellite, but we pass different situations in the past. Someone sold to us bad components. And fortunately, we tested all of them, and we detected fail in all of them. 60 components bought, 54 were damaged.
Wow.
Were not delivering the proper specifications. And that was, in my opinion, on purpose. So this is attached to this kind of difficulties to access this kind of high quality components. The issue is also having staying in line, being prioritized, because we don't have a pushant program. We are not developing one satellite per year. We have one every 4 years in case of Brazil. I was the director of INPE that put one per year. So you saw in my presentation, 1 in 26, 1 in 27, 1 in 28, 1 in 29, and then skip and have 31 with the Chinese. So have like 5 satellites in 6 years.
Yeah.
Why I did that? Cadency. Cadence, you have to have cadence in your industry. The industry is not going to fulfill supply to you unless you prove that next year you're going to buy again, next year you're going to buy again, next year you're going to buy again. Because nobody, no investor, going to build a company to provide one solution. And if they do so, it's going to be cost your eyes. And then it's cheaper to buy outside. It's cheaper to buy it abroad. So that's why you don't have push-and programs. And don't have this kind of programs, you don't enter in the queue for satellite. Imagine competing with Elon Musk. He launched hundreds of satellites. He buy in the, like we call in Spanish, majorista, he buy in trucks of components. We buy numbers of 1, 2, 3, 10 of those, maybe hundreds. We had to, in Brazil, for our satellites, due to the restrictions, there is something that we have to buy for building 10 satellites. But that's the minimum allowed number for the supplier. And I have to buy 10 of those, even if we're going to build one satellite only. What am I going to do with the 9 others? See?
Yeah.
And then the price is up, is not proportional to the advanced programs like they have in Europe, like they have in India, like they have in China, like they are having in the United States, for instance. So developing countries have these 2 big issues. First one is the political decision to do so. So that's why political decision comes first, because the politicians has to know that you are going to have a big issue to develop in your space program, and it's going to cost, and it's not cost effective. If you make a financial analysis of that, it's going to blow up. You have to decide to put money for several times, for several decades, or for several, maybe 2, 3, 4 decades, not years, losing money. Then you can have a push-and program, a space program. But that's why we have to have a political decision that doesn't have to be defended by only one party of the society. You have to convince your society that the space program is important for them. Once you convince them, you have to have political of both sides, leftists and rightists, agreeing to have a space program. And when they agree, you have to survive to different politicians coming up to the power and shutting down this, up and turn on that, etc. Once you do that, having money is easy.
Well, thank you very much for the answer. We are going to follow your steps in Mexico, and I hope sooner than later to have a collaboration between Mexico and Brazil. So thank you very much for the answer.
Thank you.
Thank you both. Does anybody else have a question?
Me.
Yeah.
Well, my question is about, you mentioned, my name is Alfonso. I'm from Aeronautical University Querétaro. I wanted to ask about the satellite you mentioned that has the research of gravitational waves. How is this contributing to the actual research? And if it does have an important impact
Which satellite?
in your universities?
Thank you very much, Alfonso. But which satellite you mentioned? The satellite
I heard about one that was studying gravitational waves, if I'm correct.
Okay, yeah. Okay. So there's a MIRAX mission. We develop a X-ray detector. So we have an X-ray detector with measure the X-ray from whatever you want. You can point it to the sun and monitor space weather, for instance. And you will develop small, teeny tiny tiles like this, that any tile is one X-ray detector. So you have an array of X-ray detector, and you put a mask over it, a known mask, mathematically known. And then you have the X-ray coming to the mask, and as they arrive to your field of view of your X-ray field of view, which are several points, like an imager of the camera, like a camera of the satellite. So you have different points of view of X-ray, and you have the mask, so you know exactly which point of their space they are coming. So this is one of the satellites we have been developing in Brazil. This is a scientific satellite. So we developed the payload in this case, and we have the P100 satellite that is being validated with the Germans. And once it is validated in space with the Germans, you can use this platform to put our payload with our satellite. And then you're going to have one satellite flying far away from the low orbiting. We are talking about a satellite that can be as high as, it can be geostationary, it can be ecliptic orbit. The mission was not designed yet. But the point is, we're going to look not to the sun because of space weather, but we're going to look to black holes with this X-ray imager. And when two black holes collapse, you have an expansion, you have a collapsion of the mass, and you have the generation of X-ray that's associated to the collapse of these black holes. So the first thing that you see is the X-ray, and afterwards, you then see the gravitational waves that was proposed by Einstein, and they were detected in 2017, and they gave LASCO, the consortium LASCO, the Nobel Prize of Physics in 2017.
Thank you for answering my question.
Thank you. We have time for one last question. Who would like to ask something? No one? Okay. Well, if no one has another question. I want to thank you, Dr. Clezio, again. Thank you very much. Amazing talk, amazing work you have done. Congratulations, and see you next time. Thank you, everyone.
Thank you very much. Thank you for all for attending. It was a pleasure. I hope to see you in Mexico next time I was there. I've been twice in Mexico, but probably gonna meet some of you during the collage meet in Peru next year.
Yeah, of course. Yeah.
Thank you very much. We'll see you soon.
Thank you. Bye-bye.
Bye.